Welcome to the lecture on 3.4. Today we're going to talk about real zeros of polynomials. Let's start with the rational zeros theorem. If the polynomial p of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 all the way down to a1x plus a sub 0 has integer coefficients where a sub n is not equal to 0, then every rational zero of p is of the form p over q, where p and q are both integers, and p is a factor of constant coefficient a sub 0, and q is a factor of the leading coefficient a sub n. Now, I know this is a lot to take in. Basically, what we're saying here is that if we have a rational zero of this polynomial, meaning that when you plug that 0 in for x, you get 0 on the right here. If that 0 is a rational 0, then the rational number is going to be of the form p over q, where p is a factor of a sub 0 and q is a factor of a sub n. Right, I'm going to prove this to you very quickly. If you want to skip the proof, you're more than welcome to. This one is probably one of the least important ones. Let p over q be a rational zero in reduced form of the function p of x. Then a sub n p over q to the nth power plus a sub n minus 1 p over q to the n minus 1. This would be as if we plugged in p over q for x here. All the way down to a sub 1 p over q plus a sub 0 is equal to 0. All right, so what I'm going to do first is multiply both sides by q to the nth power so that I can eliminate all of the fractions. Right, it would eliminate this one, and we'll have some left over here. But if we multiply both sides by q, 1 by q to the n, then all the fractions will go away. We will have left over. So we would end up with a sub n p to the n plus a sub n minus 1 p to the n minus 1 q, a sub 1 p q to the n minus 1 plus a sub 0 q to the n 0. And when we distribute this, notice that we don't have anything to cancel with in the constant term a sub 0. So a sub 0 times q sub n will just end up being a0q to the nth power. A sub 1, there's only one q in the denominator. So only one of the n q's that we have here is canceled, and we're left with n minus 1 q's left. So after we do that, we subtract over the a sub 0 q to the n, like that. And we can factor out, after we've subtracted that over, then every single term on the left has a p. So I'm going to factor that out in this step as well. Factor out a p. And what's left is a sub n e to the n minus 1, a sub n minus 1 e to the n minus 2 q down to a sub 1 q to the n minus 1 is equal to, and then on the right I still have just negative a sub 0 q to the n. Right. Now, think of this entire thing as a number. We have a number here times p is equal to a number times q to the n. Now, if we remember our factorizations, and we also remember that p over q was in reduced form, what that means is that p and q share no factors. That means that p has to be a factor of a sub 0. It must be a factor of a sub 0. This then implies what we want to show. P is a factor of a sub 0. We can make a similar argument that will show that Q is a factor of a sub n. And that's really all I want to show in the proof. Go ahead and do an example of this and why this is beneficial to us. I mean, it does help a little bit. It's not the most important theorem in the class. List all possible rational zeros of p of x is equal to 2x cubed plus 4x squared minus 3x plus 3. The theorem says that all of the rational zeros will have the form p over q. P is a factor of 3, q is a factor of 2. Remember, q is a factor of the leading term, p is a factor of the constant term. So if I'm just listing all the possible rational zeros, we need to know what the factors of 3 and 2 are. Start with the factors of 3. So what are the factors of 3? Oh, we have 1 and 3. Then we need the factors of 2. What are the factors of 2? That will be 1 and 2. So all of our rational zeros will be of the form one of these numbers divided by one of these numbers. So we're going to list all the possible combinations. So the possible zeros will be plus or minus 1 divided by 1, plus or minus 1 divided by 2, plus or minus 3 divided by 1, and plus or minus 3 divided by 2. So this is it. These are all the possible rational zeros of this polynomial. Now, it is possible that none of them are actually zeros of the polynomial. We could have purely irrational zeros for this polynomial. It's unlikely. Remember, we're only listing rational zeros. It is possible that we have irrational zeros as well that we can't list here. So finding rational zeros, I'll give you a little bit of a step-by-step guideline here. 1, list all the possible zeros, like we did in the previous example. 2, divide using synthetic division. So if we're to factor this polynomial, we would take the factors that are the rational zeros that we discovered and try them one by one by using synthetic division. And 3, repeat. We're going to repeat this process until we find all of the rational zeros that a polynomial has. Let's do an example of trying to factor a polynomial down, and I'll show you this process that we just outlined there. Factor the polynomial p of x equal to 2x cubed minus 3x squared minus 11x plus 6. So what I want to do is I want to find the factorization of this polynomial. Basically, I want to list it into its smallest polynomial factors. So start by listing all of the possible rational zeros that we can have. Remember, rational zeros are going to have the form p over q, where p is a factor of 6 and q is a factor of 2. So I need to know what the factors of 6 and 2 are. Factors of 6 are 1, 2, 3, and 6. And the factors of 2 are 1 and 2. So the possible zeros that we can have will be plus or minus 1 divided by 1, which is just 1. 1 divided by 2, plus or minus 2 divided by 1, which is just 2, plus or minus 2 divided by 2. Now remember, 2 divided by 2 is the same thing as 1, which we've already listed, so we don't need to list it again. Plus or minus 3 divided by 1, which is just 3. plus or minus 3 divided by 2. Plus or minus 6 divided by 1, which is just 6. And plus or minus 6 divided by 2, which is 3. And we've already listed 3, so I don't need to list that one again. So these are all the possible zeros that we have, the possible rational zeros that we have. Okay. So the next step is to use synthetic division to figure out which ones are actually zeros of the polynomial and which ones are not. So let's start with 2. So the one that I'm guessing right now is sort of a guess and check problem now. You get better at it as you practice more. I'm trying to check if x minus 2 is going to be a factor of this polynomial. Now I could do long division, but synthetic division is much faster when you have it in the form x minus something. Now I'm going to list out the coefficients of my polynomial, i.e. this is my dividend and this is my divisor, if you remember the terms from the previous section. 2, -3, -11, and 6. Remember, this is x cubed, this is x squared, this is your x term, and this is your constant term. Now, if x minus 2 happens to be a factor, and we get a clean factorization here with a remainder of 0, then we would say that x minus 2 is a factor of this polynomial, and we would have an x squared term here. Now I'll show you that when we get to it. So we bring our 2 down. Do 2 times 2 is 4. We add, we get 1. 1 times 2 is 2. We add, we get a -9. -9 times 2 is -18. And we get a -12 here. So notice that this is our remainder. This is a remainder and it's non-zero, which means that x minus 2 does not factor into this polynomial. So I can eliminate positive 2 from the factorization. So this is, remember, x minus a positive 2. This is how we do it. So 2 is not a 0 of this polynomial, which means x minus 2 is not a factor. So I have to start over now. So I list out my polynomial coefficients again. 2, -3, -11, and 6. But now I have information. 2 is not a factor of x minus 2 is not a factor of this polynomial, so I can eliminate 2 from my guessing process. I can also eliminate it from any future process for this polynomial. And I'll show you what I mean in a second. So let's try -2 instead. Try using -2. We bring the 2 down. -2 times 2 is -4. We add, we get a -7. -2 times -7 is +14. We add, we get a 3. And 3 times -2 is -6. And we add, we get a 0. So notice that we have a remainder of 0. Now, since we have a remainder of 0, that means that x plus 2 is a factor of this polynomial. So we can keep that as a factor. And then we can move on to something else. Now, I want to note something very quickly before I erase it. We can rewrite this polynomial p of x is equal to 2x cubed minus 3x squared minus 11x plus 6. And this polynomial will factor into x plus 2 times the remaining polynomial here. Remember, this is our remainder. This would be our constant term. This is our x term. This is x squared. So we would have 2x squared minus 7x plus 3 as our remaining polynomial. noting that x plus 2 is a factor of this polynomial. This is the quotient, right? So if we can factor this further, then we would get the full factorization of p of x. So what I'm going to do, instead of erasing these values, I am going to just use them again. So I'm going to use these as my entry point because I already have the coefficients of this polynomial listed here. I'm going to start another synthetic division process. Now, what I'm going to test to see if we have another factorization is going to be x minus 3 as a factor. Is x minus 3 a factor of this polynomial, which would then mean that x minus 3 is also a factor of p of x? Remember, this polynomial is a factor of p of x as well, so if x minus 3 is a factor of this polynomial, then it's also a factor of p of x. You'll get the same factorization no matter which order you choose. So our process is going to be starting with 2 coming down. 2 times 3 is 6. Add, we get a -1. 3 times -1 is -3. Add, we get a 0. So x minus 3 is a factor of this polynomial, which then means it's a factor of p of x. Because, remember, this is a factor of p of x, and x minus 3 is a factor of this. Right? So what we're saying here now is that p of x is equal to 2x cubed minus 3x squared minus 11x plus 6. We found our first factor, which was x plus 2. So this polynomial factored into x plus 2 times the remaining coefficients here for our other polynomial. So 2x squared minus 7x plus 3. And then we found that x minus 3 is in fact a factor of this. So this polynomial will factor into x minus 3 times whatever's left here. This is our constant term, this is an x term, so we would have 2x minus 1, this. And we just carry our x plus 2 down. So the full factorization of p of x is x plus 2 times x minus 3 times 2x minus 1. And that will be the process for factoring a polynomial using synthetic division. I will note that in the middle here, I didn't reference any of these numbers, but notice how our constant term changed from a 6 to a 3. So actually, if we were to look for factors of this polynomial, we would only look at factors of 3 divided by factors of 2. So if we hadn't factored it yet, and we wanted to try to factor this polynomial, we could eliminate 6, we could eliminate 2 completely, and we would only have these 4 numbers. So it would be plus or minus 1, plus or minus 1/2, plus or minus 3, and plus or minus 3/2, because those would be the factors of 3 divided by the factors of 2. Now, I didn't reference that, but that is part of the process that you can use. Try one. Find all possible zeros, then factor p of x is equal to x to the 4th minus 5x squared plus 4. We'll note here that zeros can be reused. So on this previous problem, once we got to here, we couldn't reuse -2 only because 2 is not a factor of 3. But if this turned out to be a 6 and 2 is still a factor of 3, we could check this 0 again. We could list a -2 here and try again. It is possible for that to happen. And that would mean that that factor has a higher multiplicity than 1. I will note also that you're missing an x cubed term and an x term, so you need to put zeros in as placeholders for those coefficients. And the next thing we're going to talk about is Descartes' Rule of Signs. Let P be a polynomial with real coefficients. 1. The number of positive real zeros of P of x either is equal to the number of variations in sign in P of x, or is less than that by an even whole number. And 2. The number of negative real zeros of P of x either is equal to the number of variations in sign in P of negative x, or is less than that by an even whole number. Now I realize this is a bit wordy and it's a little bit confusing. It's a lot of words to say a pretty simple concept. Example, find the possible number of real zeros of P of x is equal to 12x to the 5th plus 4x to the 4th plus 3x cubed minus 10x squared minus 3x plus 21. Okay. Now when we look back at the theorem here, or the Descartes Rule of Signs, when they say the number of variations in sign in P of x, what they mean is the number of sign changes from term to term. So we have x to the 5th. You write it in descending order of degree. So power of 5, power of 4, power of 3, power of 2, power of 1, power of 0, of course. And then we go term by term and we look at the number of sign changes. So positive sign, so there's 0 sign changes so far. Positive sign, here's a sign change. It changes from positive to negative. So 1 sign change. Negative to negative is no sign change, and then negative to positive is a second sign change. So we have either 2 or 0 positive real zeros. We had 2 sign changes, and then if we go back to the rule, it's either equal to the number of variations in sign, i.e. the number of sign changes, or less than that by an even whole number. So 2, and then if we subtract 2, because that's the smallest even whole number, we get 0. So it's possible that it's 2 or less than 2 by an even whole number, and even 2 is an even whole number, so we could also have 0 positive real zeros. Now, if we want to look for the negative real zeros, then we don't look at P of x, we look at P of negative x. And if we plug in a negative, we get negative 12x to the 5th plus 4x to the 4th minus 3x cubed minus 10x squared plus 3x plus 21. And we count the number of sign changes again. So the negative deals with P of negative x, the positive is P of x, just normal P of x. So we start here, we have a negative, we change to positive, that's 1 sign change. Positive to negative is a second sign change. Negative to negative, negative to positive is a third sign change, and then positive to positive is nothing. So we either have 3 or 1 negative real zeros. So we have either 3 or less than 3 by an even whole number. Less than 3 by 2, 2 is our smallest even whole number, is 1. So 3 minus 2 is 1, so we can have either 3 or 1 negative real zeros. 1 minus 2 would be a negative 1. That's not a possibility here. All right, the next thing that we're going to talk about is the upper and lower bounds theorem. For the definition, we say that A is a lower bound and B is an upper bound for the zeros of a polynomial if every zero C of the polynomial satisfies that A is less than or equal to C, C is less than or equal to B. So basically what we're saying here is that we can restrict the possible zeros, and these are only rational zeros, but we can restrict even irrational zeros with upper and lower bounds. So notice here that 3 is is the maximum 0 for this particular polynomial. So 3 would be an upper bound on this on the zeros for this polynomial. And we can also see that -2 is the smallest 0 for this polynomial. So -2 would be a lower bound. -3 would also be a lower bound, but -2 is actually the largest lower bound. Basically, any number less than -2 would be a lower bound for the zeros on this polynomial. The upper and lower bounds theorem. Let P be a polynomial with real coefficients. If we divide P of x by x minus b with b greater than 0 using synthetic division, and if the row that contains the quotient and remainder has no negative entry, then b is an upper bound for the real zeros of P. 2. We divide P of x by x minus a, where a is less than 0, using synthetic division, and if the row that contains the quotient and remainder has entries that are alternatively non-positive and non-negative, then a is a lower bound for the real zeros of P. Now we'll note here, when we talk about alternatively non-positive and non-negative, what this means is that if you get a 0 in that row, I'll show you an example in a second. But if you get a 0 in that row, then it counts as both positive and negative. So I'm going to make a note here to remind you. For this theorem, we consider 0 to be both positive and negative. All right, let's jump into an example to explain what this theorem is saying. Back to the polynomial. So if we have the polynomial P of x is equal to x to the 4th minus 5x to the 3rd plus 6x squared plus 4x minus 8. We can start by looking for the possible rational zeros. We do that by taking the factors of 8 and dividing by the factors of 1. And we would then get that the factors of 8 are 1, 2, 4, and 8. The factors of 1, of course, are just 1. So our possible zeros, I should say the possible rational zeros, are plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. These are the only possible rational zeros. Now, it's not to say that they are the only possible zeros, but they're the only possible rational zeros. So let's start with -2. And remember, when we do synthetic division, we're looking for factors. I like to write my factor off to the left so that I know if it will be so I know to rewrite it when I'm done, if it is in fact a factor. -2 goes in the box. The coefficients of the polynomial are listed here. So 1, -5, 6, 4, -8. -2 is a possibility, so let's try it. 1 comes down. -2 times 1 is -2. Add, we get a -7. -2 times -7 is positive 14. Add, we get 20. -2 times 20 is -40. Add, we get a -36. -2 times 36 is positive 72. We add, and we get a 64. I want you to notice this is the row that contains the quotient and the remainder. Notice that they alternate signs. We have a positive, negative, positive, negative, positive. What that means is -2 is a lower bound. So from this theorem, if we divide P of x by x minus a using it synthetic division, and if the row that contains the quotient and remainder has entries that are alternatively non-positive and non-negative, so they alternate positive and negative, then that number is a lower bound. So what this does then is not only does it eliminate -2, from contention as a factor because we don't have a remainder of 0. It eliminates -4 and -8 from contention. Now, I'm going to have to contrive one here for you, but I'm going to give you a 5 here. We'll do x minus 5 would be the factor. Obviously, this will not be a factor of this polynomial. I'm specifically doing this to show you that we get an upper bound. How do I know that this will not be a factor? You should ask yourself that and try to think about it for a few minutes. Pause the video if you need to, but the answer is that 5 is not listed in the possible rational zeros, and since 5 is rational and it's not listed here, it's not a possibility. Because it's not a factor of 8. 1 comes down. 1 times 5 is 5. We get a 0. 0 times 5 is 0. We add, we get 6. 30. Add, we get 34. 34 times 5 is 170. And then we add and we get 162. Notice that we have all positive entries except for 0. But remember, 0 is both positive and negative. For this theorem, we consider 0 to be both positive and negative. So since it can be positive, and it fits with the pattern of the first one here, dividing p of x by x minus b, where p is greater than 0, using synthetic division, and if the row contains the quotient, the row that contains the quotient and the remainder has no negative entry. So it doesn't have a negative entry. 0 is considered positive. So it has all positive entries, including 0 here. We can say that 5 is an upper bound. So that would actually eliminate 8 entirely, because 8 is bigger than 5, and we know that our zeros are bounded by 5. So we can eliminate 8 because it's bigger than 5, and 5 is an upper limit on the possible zeros. Meaning that the zeros will be no higher than 5. Since 8 is higher than 5, it's not a possibility. So now I'm going to go ahead and factor this correctly for you. I want to emphasize a point, so I'm going to do that. Now I'm going to do x minus 2 as a possible factor. So I want to note something that I noted before for your try 1 problem. Bring our 1 down. 2 times 1 is 2. We add, we get a -3. 2 times -3 is -6. We add, we get 0. 2 times 0 is 0. 4. 4 times 2 is 8. And we get 0. So since we have a 0 here, we know that x minus 2 is a factor. So I'm going to list it off to the side as a factor of my polynomial. We write it in green, actually. Okay. Now, if you remember during your try 1 problem, just because we used x minus 2 as a factor already doesn't mean we can't reuse it. So I'm going to reuse it here and see if it goes into the new polynomial. See if it goes into p of x multiple times. This would be x minus 2 again. One comes down. 2 times 1 is 2. Add, we get a -1. 2 times -1 is -2. Add, we get a -2. 2 times -2 is -4. And notice we get a 0 again, which means that x minus 2 goes into p of x again. So x2 will be a 0 of multiplicity 2 as of right now. Now again, it is possible that we get another 2. It is possible. Doesn't mean we will, but it's possible. So let's check. X minus 2 again. 1 comes down. 1 times 2 is 2. Add, we get 1. 2 times 1 is 2, and we get another 0. So it goes into p of x a third time. So we actually end up with x minus 2 having multiplicity 3 in the factorization of p of x. And then the last factor is x plus 1. As we can see here, this would be our constant term, this is our x term, so the last factor is just x plus 1. Okay. So our final factorization of p of x would then be x minus 2, the third power, times x plus 1. This third power means that it goes into p of x 3 times. X minus 2 goes into p of x 3 times. If you FOIL this out, all out, you'll get back to the original polynomial. Now, these are kind of tricky sometimes when you have to reuse a number in your synthetic division. So be careful with that. A lot of students forget that, and they just move on to a different number. You don't necessarily need to move on. I want you to try one now. Find the upper bound and the lower bound for the real zeros of the polynomial p of x is equal to 2x cubed minus 7x squared, 4x plus 4. Find any upper bound. It doesn't matter what the number is, just find any upper bound. You'll also find a lower bound for this polynomial as well, for the real zeros. Now that would just be, like in the previous example, finding our -2 and our 5. If you found a lower bound, it means that this line in the synthetic division, where the quotient and the remainder are held, will alternate in sign. That's for lower bound, and upper bound, it will be all non-negative. All right, that's going to be it for today. I will see you all in the next lecture.